Okay, here we are, starting part 3 of this course. First part, we sort of focused on the solar system, our solar system. Second part, thinking about stars in general, their lifetimes, how they end their lives. The last part of the course, we're going to go sort of big scale and start thinking about our galaxy here, and then talk more about galaxies in general, and then sort of this space between galaxies, and then the really big sort of structure of the universe, or how galaxies are arrayed, and the kind of stuff we think that's playing a big part in how the galaxies and the universe overall end up like they are now. So this is part 1 of the lecture about our galaxy, Milky Way. And just like when we talked about our solar system, we found out our solar system is not all that different from most other solar systems. It's a pretty standard thing. A star, planets formed around it. We'll also find something similar for our galaxy. Our galaxies are like a lot of other galaxies. Then again, there's a good amount of binary star systems. It's a bit different than our solar system, or even 3-star systems or 4-star systems. In that same way, galaxies, there's a lot like the Milky Way galaxy, but there's also other ones for other types of galaxies that we'll see too. We use our galaxy, the Milky Way, to sort of start our exploration of galaxies in general. There it is. It can be a little bit confusing because when somebody refers to the Milky Way, you might be referring to seeing this stuff in the sky, or it might be referring to our galaxy broadly, or the whole galaxy. So this kind of cloudy sort of thing that we can see in the night sky, at least when it's not a lot of light pollution, from many parts in the world, most parts of the world, you can see something that looks like this in the night sky. And this turns out to be like us looking along the disk, or along the plane of our galaxy. So we were calling this the Milky Way, and once we found out that this was just kind of one sort of view looking out into our galaxy, calling our whole galaxy, or naming our whole galaxy after the same thing we call this. This is part of our galaxy. The text actually has some interesting things to note about different cultures' interpretations or views on this structure in the night sky. I recommend going and reading that if you're interested. So we're in the galaxy. That's kind of what we see when we try to look out, at least along the plane of the galaxy. The early sort of pictures or maps or diagrams, whatever you want to call them, that some people in sort of the more modern era of science at least tried to construct the galaxy, well, as you might guess, at first were kind of incomplete. So this diagram is a representation of something that a scientist named Herschel, he was like a husband and a wife or something, but they attempted to make like a map or this sort of picture of all the stuff around the solar system or around our sun. And in that way, get a picture or a diagram of what the stuff we were in was. Which turns out to be, we're in a galaxy. I don't think they really knew that galaxies existed at that point. But anyway, they were trying to look out and basically just map where all the stars were around us. And in doing so, they came up with a picture kind of like this, sort of like a cross-section of the space that we're in. And when they looked out, they saw a lot more in the sort of line across the sky, right, along where that Milky Way is in the sky, and less so when they looked above and below it. And so the picture they ended up coming with was that our galaxy, or the space that we're in, is sort of disc-shaped, right? Most of the stuff around us is arrayed in kind of a disc-like shape, flat, circular kind of shape, which turns out to be sort of correct. We'll get more into that later, but it's not necessarily just the disk. From what they could see, it looked like we were sort of near the edge of that disk. That turns out to not really be correct, and partly they were just limited by the instruments of their time. The telescopes that they were using only allowed them to see objects that were at most about 6,000 light years away from us. Where nowadays we know that the whole galaxy is something like 100,000 light years across. So they were only seeing a little patch, not that little, but a fairly small patch around the sun. So the shape that they ended up getting and where they thought we were within the disk is a bit biased because they're only getting a small portion of the bit later on, this other scientist, astronomer, Shapley, sort of expanded our view or our sort of map of where stuff was around us. And partly what he was doing was trying to map out the locations of globular clusters. So we talked about globular clusters a bit a little while ago when we were thinking of like the age of stars and like the lifetime of stars in general. Globular clusters, I told you at that time, were these really old collections of many, many stars, and those clusters, most of them tend to be out of the plane of the galaxy. So they're still attractive, they're still kind of part of our galaxy, but they're not in the plane where most of the other stuff is. And so when he looked and kind of started to map out all those things, he started to get a much larger picture where the diagram on the left there, that little black area, the dark area, that was the old picture, the old space that the Herschels had mapped. But he started mapping all these globular clusters. They are further away for sure, but they're also not necessarily just in the disk, right? Just in kind of a flat or flatter region. They can be very far out, or far away from like where that plane is in the sky, the Milky Way. And in fact, nice tie-in, he was using the pulsating variable stars I told you about that we use to map the distance or say how far away it is. So Shapley was using a certain kind, which I told you a little bit about, the RR Lyra or Lyra stars. So that's what he was using about the distances, just as an interesting side note. And this is one of those globular clusters I think I showed you before, M80. So basically by looking at these things and using the pulsing variable stars, you could determine that actually there's a decent amount of stuff not necessarily in just this disk anymore, and also much further away than that 6,000 light years that the Herschels can see. So part of what made it difficult to see much further out than a few thousand light years or several thousand light years was that there's a good amount of dust and gas just floating throughout the galaxy. That's that interstellar medium that I told you about when we were talking about the stuff in between the stars. There's a good amount of that stuff, and it's sort of like trying to look at stars in the night sky. Right? If you look straight up, we're looking through the atmosphere when we look, so there's a decent amount of gas in the way, but we can still see stars fairly well if you look straight up. However, the further you look towards the horizon, the more and more atmosphere that light has to travel through before it gets to you. So when you get closer and closer to the horizon, there's more and more gas and dust in between you and the star, and you tend to see a lot less stars. That's why the stars are a lot fainter, and there's just a lot less of them you see along the horizon. So this is the same thing. You just try to look further and further out from our solar system, and you're essentially trying to look through more and more gas and dust. And visible light just doesn't tend to travel more than a few thousand light years through the interstellar medium. So that's like if you're looking along the plane of the disk, because most of the gas and the dust in our galaxy is still within that plane. Right? If we look like out of the plane of the disk, then not as much of that in our way. But then we're looking out towards like other galaxies. So that makes it difficult to see things very far in visible light. However, as I've told you about multiple times, we use all parts of the electromagnetic spectrum in order to do astronomy. So we collect electromagnetic radiation of all these varieties, not just visible light. Some other ones that are very useful in this context are infrared and radio waves, because both of those things tend to travel through the interstellar medium a lot better. As an example, this is looking at, I don't recall which nebula this is exactly, it's part of a nebula, and if you look at it in the visible range, the gas and the dust that makes up the cloud of that nebula, you don't really see anything, you don't see into it, you don't see past it, right? Visible light gets blocked by all that gas and dust. However, if you look in the radio, we can see through that cloud of gas and dust. And in fact, if you look around, outside of where that cloud, or that dense kind of cloud is, right, you see a lot more stars in general too. And that's because in the visible range, there's still a lot of this dust around throughout that whole image in the visible range, and it's blocking light from the far stars behind it. Whereas in the radio, that dust doesn't affect the radio waves coming through very much, so we get a lot more, we see a lot more stars in the background in this radio image. So by using infrared light and radio waves, light in the radio part of the spectrum, we've been able to see much further through the galaxy. It's given us a much more detailed picture of what the whole structure of the galaxy looks like. And as you might know, this is roughly what our present picture of our galaxy, the Milky Way galaxy, what it is. Right? It's a spiral, so the central, more dense area, and there are these sort of arms come off of that central area, and it's all sort of swirling around. So yeah, the image on the left is if you were somehow able to be outside of our galaxy and looking down on it. You have to be very far away in order to see a picture like this, but we can imagine. And then the picture on the right here is if you were looking at the galaxy like edge on. So you're outside of the galaxy maybe, but you're like looking just along the plane of the galaxy, or the galactic plane. So of course we've come up with names, or we've named some of these arms of the galaxy. Right? Some of them are shown on there. Cygnus arm, Perseus arm. Also, one of the main features of the galaxy is that the center is not like a completely sort of round thing. It looks like, or it seems that the density of the stuff in the center is actually kind of arrayed in a sort of bar, like along a line almost, the center of the galaxy. So that's what that central bar is pointing out. The really bright, like yellowish part, just a sort of bar. So also shown on here is the location of the sun. The sun is in sort of a minor arm of the galaxy, right? Not one of these major ones. We call the minor one spurs. See when the sun is there. It's actually more like halfway between the center and the edge of the galaxy. More specifically, it's about 26,000 light years from the center of the galaxy. And from the center to the edge is about 50,000 light years. The whole way across, about 100,000 light years. And then if we think about looking at like the edge-on picture, you know, there's a certain thickness to our galaxy, at least of this like disk stuff of the galaxy. And you can kind of differentiate between like a thin disk and a thick disk. In general, the density of stars falls off, or it gets less as you move away from like the plane of the galaxy. So in that like thin disk is much more dense in general, more stars within, you know, about 400 light years from the plane of the galaxy. And then the thick disk, it goes out to like a few thousand light years wide, and just less dense, less stars overall. So currently it seems like the sun is something like 70 light years from the plane of the galaxy. I don't know if we're above or below in this picture, but we're like off, a little bit off to the side. Still inside like this thin disk though. And as it's also shown in this image, there's other dots there, and those are probably indicating like globular clusters or just old stars, right? So not everything in the galaxy is in that disk. It sort of just gets less and less stuff the further away you get from the plane of the galaxy. And also, some of these numbers, I don't know, it can vary a little bit. Basically, the thin disk, or the most dense part of our galaxy, something like a few to several hundred light years thick. And then the thick disk, well, there's still quite a lot of stuff, but it's less dense than the thin part. It goes out to something like a few to several thousand light years. So definitely like most of the stuff that makes up our galaxy, most of the gas and the dust and the stars are all within this like thin and thick disk area of the galaxy. But there's still a decent amount of stuff out here. And that, I should point out, is just the stuff that actually emits electromagnetic radiation. It emits light of some kind. We'll see a couple times throughout this lecture that there seems to be a lot of other stuff there that doesn't emit any kind of light. So this is an actual like collage or whole survey of images that were taken in the infrared part of the spectrum. So looking towards the center of the galaxy, it's kind of cool. You actually just see sort of what the center of the galaxy, or what our galaxy looks like when you look towards the center. Really bright in the middle, and it kind of bulges a little bit, and then there's a decent amount of stuff that's still really bright, but it's in this like disk around that center. Right? So that like plane, that line, you can kind of draw through all this stuff. That's what we call like the plane of the galaxy, or the galactic plane. And yeah, it turns out something like 2/3 or like 66% of all the stars in our galaxy lie within about 1,000 light years of that. So up and down in about 1,000 light years. Some other sort of features, like the stars that are closer to the plane tend to be younger stars, whereas stars we find further and further away from the plane, or further and further out, tend to be older. So our sun is like, we say 4.5 billion years old or something like that. It's still definitely in the disk or within this 1,000 light years from the galactic plane, and it's not necessarily a young star anymore, but it's still maybe on the younger side than old. Like old stars, like 10 billion years old probably. Yeah, and like I said, that center is not necessarily a flat disk when you get towards the center, and it seems like it's actually kind of a bulge here, and it's not even just a sphere. It seems like it has more of this like peanut sort of shape, where it's like two lobes, a little bit thinner in the middle. So we call that the bulge. Really clever name. There's a lot of clever names coming up here. And as I said earlier, the center also doesn't appear to be particularly round. That peanut shape also means it's like a bar if you look down on it. So this central area, we also call this central bar, and given that our galaxy is spiral shape, turns out, put those two things together, you would call our Milky Way galaxy our spiral galaxy. So there could be spiral galaxies that don't necessarily have that bar. And we'll get into more kinds of galaxies later on too. There are galaxies that aren't really spiral at all. Yeah, a little more about that later. Oh, right. So here we go. I have some examples of two spiral galaxies where the image on the right in B here has a pretty clear, or pretty distinct sort of like bar or almost like rectangular central area. Versus if you look over on the left side in A, there's not. The central area is pretty symmetric. It's like circular. Basically, we try to like draw a line to encompass the really bright area in the very center of these galaxies. On the left, you can pretty much draw like a little circle. But on the right, you kind of have to do a little like rectangular shape. So this one on the right is like a bar, or what we call a barred spiral. The left is just a regular spiral, or unbarred spiral galaxy. This is just another sort of picture of the galaxy, or a really simplified diagram. Right, we have like the center of the galaxy. Around that center is this kind of bulge, and that's even been simplified here because, like I said, the bulge is sort of more like a peanut kind of shape. And then around, or through sort of the center, and then around in this plane, there's this kind of thin disk, most densely populated area, stars and the intergalactic medium and all that, just most of it there. And then outside of that, you have a thicker disk around all that. It's a bit less dense, a bit less stars, a bit less gas and dust. But then, as I've said, outside all of that, there's still more stars and like groups of stars, like globular clusters, that are kind of all around in somewhat spherical shape around the galaxy, around the center of the galaxy. So like globular clusters and also just very old stars we find in these sort of half circles above and below the plane of the galaxy. So we've termed these areas like the halo of the galaxy. It's a sort of spherical shape all around the galaxy. I think I've mentioned the halo before, and I might have said it incorrectly where I said that we call each side or each hemisphere, like the top and the bottom, are each called halos. If I said that, that was mistaken there. It's the whole sphere around the galaxy is called the halo. So as you start to think about the stuff in the halo, and in general looking at like the far outer reaches of the galaxy, we start to get sort of a conundrum or puzzling thing start to show up, where if we use our understanding of gravity to say how things in like the halo of the galaxy and how things like towards the outer edges of the galactic plane, how those kinds of things should revolve around, particularly like how fast they should be moving around as the galaxy kind of swirls. If we use our regular understanding of gravity to do that, we get one answer, but when we go and look out and start to be able to measure these things and their speeds and how they're moving, we found that things in general are moving much faster than they should be. Towards the very edge of the galaxy, objects way out there, stars and like the gas and the interstellar media and all that stuff, is still moving around a lot faster as it goes around the galaxy than we would expect, given sort of our normal picture of gravity and how much mass, how much stuff there appears to be that makes up the galaxy. So our current sort of resolution to that, and we'll say more about this at the end of the lecture, is to postulate that there's actually more stuff, there's more matter all around the galaxy, throughout the galaxy and halo, all that stuff. It's just matter that doesn't emit any light. We never see it. The only way that we tend to think it's there is from its gravitational interaction. The fact that it changes the way that all this stuff is orbiting around. And so since it doesn't emit any electromagnetic radiation, doesn't emit any light, we call it dark matter. Back to that shortly. Say a little bit more about the galaxy first and its structure. This is a more detailed picture of what we think our galaxy looks like. Again, we can't like get out of the galaxy and look back and take this picture. It would take tens, if not hundreds of thousands of years moving at the speed of light to get far enough away to turn back and take this picture. So this is a creation, possibly a computer model, based on all of our observations so far, or most of the observations so far. This is what we think our galaxy looks like. And again, it has that central area. The central area is sort of this rectangular or bar shape, and then there's these arms that are swirling around, or spiraling around. This is our barred spiral. The position of the sun is also indicated on here. Again, it's in that Orion spur, smaller sort of arm-like thing. Yeah, and each one of these, I think I mentioned it or said it already, but we call these things that make up the spiral arms, the spiral arms. And there's a good number of them. There's other stuff on here. There's this like coordinate system on here. We need to worry too much about that. But just to say, I guess, that it's similar to like how we use longitude and latitude in order to specify like how far north or south or how far east or west something is, or sort of position of something on the Earth. We have a similar system for specifying like the angle here, but in terms of the position of the sun and the center of the galaxy. So these are indicating, I think, what we call galactic coordinates. We're not really going to worry about that though. This is just a bit more about like our position, specifically like the orientation and the movement of our solar system within the galaxy. But I mentioned already, we're about halfway between the center and the edge of the galaxy. And it turns out, all the stuff is swirling around. So the whole galaxy kind of rotates around. And our sun and our solar system and all the stuff in our solar system, the Earth, planets, pretty much all of us together are moving around the center of the galaxy at about kilometers a second, really fast. However, the galaxy is enormous, and so it still takes about 225 million years for our solar system to make one revolution around the galaxy. And so just like for the Earth, we call a year on Earth the time that it takes for the Earth to go all the way around the sun and come back to where it is. A year in the galaxy, or a year for our solar system, is 225 million years. Long it takes to go all the way around. And since our solar system is about 4.5 billion years old, it works out that we've gone around the galaxy, or our solar system, our sun, planets at least, have gone around the center of the galaxy about 20 times. So our whole solar system is only like 20 galactic years old. Then the last thing I wanted to point out is just that, when we're talking about our solar system, we have like the sun in the center, and all the planets are orbiting around, and they're all orbiting in a pretty similar plane, right? I told you about what we call the ecliptic. That's like the plane that gets drawn out by the Earth's movement around the sun, right? So there's that plane, and all the other planets are fairly close to that plane. They're all orbiting that. It turns out that whole plane is tilted in its motion through the galaxy. So it's not like all the planets are going like this, and then all together we're moving around the galaxy like that. In fact, the whole plane of the solar system is about 60 degrees off the plane of the galaxy. So it's something more similar to like that very simple image I put down there, which shows like the galactic plane, and then, like, very exaggerated, but like the sun and the ecliptic, or like the orbit of the planets, is very far off of what the direction or of the plane of the galaxy. And this is just a bit closer look even at like our neighborhood, which would be like that Orion spur that we're located in. There's the picture on the left there of the spur, and our sun is indicated, right? The sun on the bottom, towards like the bottom right of all that stuff. And then a number of other objects, things, are also indicated there. The Orion Nebula is actually fairly close to us, in terms of galactic sizes, only about 1,300 light years away, and it's indicated on the image there, pretty close to the sun. There's also this thing called the Rosette Nebula, which is indicated on there as well. It's a bit further away. It's almost up in the other arm, some of that Perseus arm. That's about 5,200 light years away. This is sort of our galactic neighborhood. So now we're going to get back to thinking a bit more about this problem that comes up when we try to ask, how much stuff is there in the galaxy? We could also say, or how much like matter is there? How much mass is there? How massive is the galaxy? So we can do sort of like a survey and just look and see, of all the stuff that we see, sort of estimate, how much stuff there actually is in the galaxy, and how massive is all that stuff? How much mass does all that make up? So when we do that, we look for all the matter we can see. We call this luminous matter because it gives off light of some kind, meaning it emits electromagnetic radiation. It might be visible, it might just be infrared, it might just be radio, it might also be X-ray, right? Any kind of electromagnetic radiation. Right? That's what we call luminous matter. If we try to estimate how much of that there is in our galaxy, we get a figure that's something like 100 billion times the mass of the sun, which is a lot. That's a lot of mass. 100 billion times the mass of the sun. However, as I told you, it's kind of an issue, because if it's only that amount of mass that makes up our galaxy, then we can use our understanding of gravity to say how fast something like towards the outer edge of our galaxy should be rotating around, how fast it's going to be moving around. Because it should only depend on the mass. That gravitational pull that it's feeling from all the other masses determining how fast it moves around. So towards the edge of the galaxy, we expect things to be moving much slower than they are relative to stuff towards the middle. This is a very similar output, or very similar result that we see like in planetary systems, like in our planetary system, right? The planets that are nearer to the sun, nearer to most of the mass of the solar system, are orbiting much faster. They go around a lot faster. Versus you get further and further out, like Jupiter and Saturn and Neptune. They take a long time to get around the sun. So this had to do with Kepler's third law. So we just take that idea, apply it to the galaxy, we would think that the stuff at the edge is going to go much slower. Well, turns out it's just not. Right? We look out, we observe, we find that the stuff near the edge of the galaxy is still moving very quickly. Generally, like as fast as the stuff, in this middle-ish and even towards the center of the galaxy. It varies a good bit, but still much, much faster than you would expect. So like I said, one way to explain this, at least within our understanding of physics and gravity works, is to just postulate, to say that there's actually a lot more mass there, and a lot more matter there. We just don't see it. Right? It's not luminous. It's not emitting any kind of electromagnetic radiation, so we don't detect it that way. The only effects we see from it are from its gravitational pull and the fact that it changes how fast stuff is moving through the galaxy. That's fine. We can just say there's other matter, we just can't see it. Then the question becomes, how much matter do we need in order to make sense of the way that all this stuff is revolving around the galaxy? A lot more. Yeah. Like 20 times more matter than just the stuff that we can see, just the luminous matter. So there's about 100 billion times the mass of the sun of luminous matter. We need something like 2 trillion times the mass of the sun in order to account for the movement of stuff throughout the galaxy. Which is just kind of wild, because what that's saying is that most of the matter that makes up our galaxy, we don't see, and we don't really know much about. The total mass of the galaxy is like 2 trillion times the mass of the sun, and all the luminous stuff only makes up 100 billion. Then that says that like 95% of the matter that makes up our galaxy is the stuff that we just don't know much about. Yeah. Right, so I've been telling you about the movement of stuff throughout the galaxy. Right, this is one way of visualizing the difference, or like kind of problem that we have. So this is a graph of the distance you get away from the center of the galaxy and how fast objects are moving at that distance from the center. So right very near the center can be a little bit weird, but if you get a little bit ways away from the center, right, things are moving very fast. Right? The plot jumps up really fast. And if we follow A, like the dotted sort of blue line, then things are moving really fast, but then the further away you get from the center, then the velocity or the speed of objects in their orbit around the galaxy, we would expect to drop off. Right? It gets less and less and less the further away you get from the center. So A is kind of the expected movement. We're showing the expected movement of objects and stuff around our galaxy. However, B is what we observe, or more like what we observe. This is a very simplified diagram, but it gets to the idea where close to the center of the galaxy, sure, it still makes sense. This velocity of things is going really fast towards the center, and maybe it starts to fall off a little bit, but then it actually kind of goes back up again. And for the most part, the rate that things are orbiting around the galaxy, even towards the very edge, tends to be pretty similar to what they are near the middle, or near the center. So this is the kind of plot you would call a galactic rotation curve. So you're looking at the rates that things are rotating around the galaxy and how that changes as you get further from the center. The basic idea here is the same thing I've just been telling you, is that our prediction says you go further out, things should be moving much slower. What we observe, you go further out, things aren't moving much slower. Why is that? Well, that's why we say there's probably much more matter there than we can see, or that is luminous. Yeah, so there's quite a lot there that we think is there, we don't see it. We observe it through its gravitational effects on the other matter that we do see. And this is not just our galaxy, right? Many galaxies have this same kind of behavior, where if we look at a galaxy, we estimate how much mass there is based on all the matter that we can see, meaning all the luminous matter, the matter that is emitting electromagnetic radiation of any kind. It's not enough mass to account for the rotation of that galaxy, particularly like the rotation or how fast things are moving towards the edge of that galaxy. It's currently one of the biggest mysteries in astronomy and physics. Right? What is that stuff? And as I mentioned a couple of times now, the leading theory to explain this sort of mystery, this discrepancy from what we predict and what we see, is that there's just a lot more matter around, and that matter just doesn't emit any kind of electromagnetic radiation. It's non-luminous. It's not emitting any kind of light, you can't see it, we call it dark. This is dark matter. So it's matter because it's still massive, and it still interacts or has a gravitational pull on things, and that's how we see it, or that's how we observe its effect, is its gravitational pull. And then later on we'll see there's other evidence. It's not just the rotation of galaxies or how fast things are rotating galaxies that makes us think there's just dark matter around. There are a number of other places that sort of point to the fact that there is a lot more matter in the universe, we just can't see it, or it doesn't emit any kind of light. One of those things that we'll talk about later on is has to do with something called gravitational lensing. And that has to do with like dense areas of this dark matter that seem to be like warping space-time, right? Having that gravitational effect, but still just being dark, non-luminous. And there are other theories to explain this, but so far, and for at least a few decades now, dark matter has been the one that still seems to make the most sense. Perhaps something else will come along, but right now, it's the best we got. And that is all I got for this part of the lecture. Continue talking about your galaxy and what it tells us about galaxies broadly in the next part of this lecture. So I will see you then.